Halogenation and hydrohalogenation are two closely related reactions. They have the same reaction mechanisms. In halogenation, we wind up with vicinal dihalides, meaning halogens are bonded to adjacent carbons. In hydrohalogenation, one of those carbon halogen bonds become a carbon OH bond. The regiochemistry is hard to tell when you have halogenation because both carbons get a halogen bonded to them. But when you have hydrohalogenation, the OH group goes to the more substituted carbon. And the stereochemistry is anti. So as usual, we're going to use the mechanism to explain both the regiochemistry and stereochemistry. So overall, here's the products of our halogenation reaction. And the reaction is anti. In other words, a bromine or a halogen adds to one of them adds to one side of the dual bond and the other bonds to the other side. And you can really see that when your alkene's in a ring. And so in the first step, we form this cyclic intermediate here where it's called a bromonium ion or chlorinium ion if you had a chlorine. And in it, the bromine is sharing a positive charge with the two carbons that used to have the double bond. The second bromine can't bond to the same side as the bromonium ion. It has to come in from the bottom in this example. You can see that here down at the bottom. The second bromine comes in from the bottom because the top is more sterically hindered. And so you wind up with your product. You can see it's trans when you have something that's cyclic. It's not going to be trans if this was a linear molecule or acyclic molecule, but it's easy to see how anti-addition, which happens here, turns into the trans product. All right, so for halohydrin formation, we do basically the same reaction, except that the solvent is water. You could actually use an alcohol as a solvent too, which would give you an ether. And so the same step happens first. And most of the positive charge is going to be held by the more substituted position, most substituted carbon here. And so when water comes in, it's going to go to the more substituted carbon because that one's more positively charged. And so again, we have that anti-addition, and just note that the OH goes to the more substituted carbon. So the reason that we might want to do this reaction is that we can use it to prepare an epoxide, which we will need for our next set of reactions.